Hello, today I will talk about goal-oriented skill abstraction or goal skill, a new approach in applied multitask reinforcement learning. What is applied reinforcement learning? Instead of learning by directly interacting with the environment, applied RL learns from a pre-collected datasets only. This is important when online interaction is too costly or risky, such as in healthcare or robotics. Also, it scales well. You can reuse large datasets for many tasks. Then, why multitask are? Because training on multiple tasks than once often improves generalization and adaptability compared to training them separately. But here comes the challenge of offline multitask RL, because each task has different reward and dynamics, and the dataset is fixed. We cannot simply share everything between tasks. So, how did previous approaches solve this? They, some people tried parameter sharing, special network architectures, or task-specific masks, but most of them work at the low level of actions like imitation moves rather than abstraction skills. Now, then, why do we need explicit knowledge abstraction? Let's think about how humans run. We don't memorize every single action, we summarize them into reusable skills. For example, learning to ride a unicycle, bicycle, and motorcycles all share the balance skills. Mm, this is exactly the idea behind Go skills. That is these papers. Here's a simple system overview. From the given datasets, they run both common skills and task-specific skills and build a discretely clustered skill library. Then, for multitask learning, they split each task into fixed time steps and at each step decide which skill to use. In the paper, this process is described as a goal encoder, skill quantization, skill decoder, and goal-oriented skill policy learning. The first component is the goal encoder. Here, the define a skill as a sub-trajectory with a fixed horizon h. Also, the goal is the representation of dynamic transfer from initial state to target state. So, the goal encoder maps the trajectory level dynamic transfer between initial state and the target state to a latent embedding space. One important thing is, instead of relying on reward signals, which vary from task to task, the goal encoder focuses only on state transitions. By ignoring reward, it captures task agnostic patterns. The second step is skill quantization. The embeddings produced by the goal encoder are still continuous and too many. So they apply vector quantization or PreQ to cluster similar embeddings into a infinity set of discrete skill codes. This builds a skill codebook, a library of reusable skills. Each slot in the codebook represents a prototypical skill pattern. The codebook is simply a set of prototype actors, each representing one skill. Over training, the encoder pushes embedding toward these vectors, and the vectors also move to match the data distribution. Now that we have a skill library, the question is, how does the agent know which skill to use for a given state? This is where goal-oriented skill policy learning comes in. Instead of choosing raw actions, the high-level policy chooses a skill index from the codebook every 8 steps. The policy is implemented with prompt decision transformer, which uses three kinds of prompts: return to go prompts and state prompts and skill prompts. The return to go prompt indicates how much reward is still desired. The state prompt describes the current environment state, and the skill prompt records what skill were used in the past. Using this prompt, the policy outputs the skill index, which points to the corresponding skill embeds in the codebook. And things to notify is these prompts are numbers, not natural language. Um, Once we have skill embedding, we still, oh, sorry. Once we have a skill embedding, we still need actual actions to interact with the environments. The skill decoder plays this role. It receives the skill embedding along with the recent state and past actions and something called the reached goal. The reached goal is defined as the difference between the current state and the initial state of the skill horizon. It tells the agent how far it has progressed toward completing the skill. By using the reached goal together with the skill embedding, the decoder can adjust its action dynamically rather than just playing a fixed sequence. So the skill decoder is not just the reverse of the encoder, it is a low-level police that executes skills while monitoring progress. Finally, it's about skill enhancement. In practice, some skills are common across many tasks, while others are rare and task-specific. This imbalance caused the model to favor frequent skills and neglect rare ones. To address this, they freeze the goal encoder and codebook after convergence, then apply resampling so that all skill classes are trained more evenly. They evaluate Go skill on MetaWorld. It is a benchmark of 50 robotic manipulation tasks using a solar arm in Muzco. They consider two task shoot. MT30 is a subset of 30 tasks, and MT50, which includes over 50 MetaWorld tasks. MT30 is a lighter weight and often used for faster iteration. MT50 stresses scalability and cross-task knowledge sharing. They use datasets from stack replay, spanning trajectories from random to expert quality. Near optimal includes the complete replay buffer covering higher quality behavior, and suboptimal use only the first 50 of the buffer, emphasizing noisier, less explicit trajectories. Then about other works, MTDT is a decision transformer extended to multitask, and MHMTDT so as MTDT with independent task specific heads. The prompt TDT is a DT with trajectory prompts for multitask generation, and MH prompt DT is a prompt DT with independent task specific head. MTDIF Harmodity is a diffusion-based method combining transformer and prompt learning for planning. And the final is Harmodity, that is DT with task-specific masks to mitigate gradient compression during sharing. Oh, it's last slide. Their future work, including dynamic curve, adapting skill horizons, and exploring stronger goal representations. And in my opinion about this paper, it may not be suitable for non-sequential tasks if all skills share the same time horizon age. And moreover, the first cannot refer to multiple tasks at the same time. If we could, more complex tasks could be expressed with a more compact skill library. Thanks for listening.